Hi, I'm Ashley Tyson, and this is my lab for oscillations. In this lab, we investigated the motion of a spring mass system that combines two different types of motion, vertical oscillation and swinging in an arc. Unlike a simple up and down spring system, this setup behaves more like a pendulum while also stretching and compressing, which makes the motion more complex and interesting to analyze. Using video analysis, we extracted position data for the mass over time. This allowed us to study both the horizontal and vertical components of motion. By applying concepts from oscillations, forces, and energy, we aim to understand how these two motions interact and how well we can model them using fundamental physics principles. We also developed a code to model the system computationally. The purpose of this was to generate predicted motion based on known physical parameters such as mass and spring constant, and then compare those predictions to our experimental data. Looking at our results, the horizontal position versus time graph shows a clear sinusoidal pattern. This indicates that the horizontal motion behaves similarly to a pendulum and it's periodic. The vertical position also shows oscillatory behavior, but instead of being centered around zero, it is centered around an equilibrium point that is shifted due to gravity. This is consistent with how a spring mass system behaves when gravity is acting on it. One of the key observations from this lab is that the horizontal and vertical motions are coupled. This means that the swinging motion affects how the spring stretches and compresses, and the vertical motion also influences the horizontal movement. Because of this interaction, the system does not behave like a simple harmonic motion in just one direction, and the resulting motion is more complex than either a simple pendulum or a simple spring system alone. When comparing the experimental data to the model, we observed that the model did not fully match the actual motion. This is likely due to simplifications in the model, particularly the fact that it does not fully account for the coupling between the two types of motion. Despite this, the overall trends in the data were still consistent with what we expect from physical principles. Additionally, the motion appeared to remain periodic, and the system generally followed expected physical behavior. Any small discrepancies between the model and experiment could be due to measurement error, assumptions in the model, or limitations in the video analysis. Overall, this lab demonstrates how combining multiple types of motion can create more complex dynamics while still being understandable through basic physics concepts. It also highlights the importance of recognizing the limitations of models when analyzing real-world systems.